Welcome back, everybody. In this episode 3, we are going to continue the work on the motherboard. I want to do a soft start of this motherboard, starting at 1 volt and then slowly go to 5 volts, 1 power rail at a time. But first, I'm measuring the resistance of the leads of my bench power supply. Look at that, it's 1.1 ohm. If I subtract the resistance of the multimeter's leads, which is about 0.2, 0.3, let's say 0.2. So we have 0.9 ohm in that first lead. Now I'm going to measure the resistance of the other lead of the power supply. I will explain in a moment why I'm doing this. 1.1, 0.9 ohm. So minus 0.2 or 0.3, we go to 0.7 or so. So this is a small resistance for the PSU leads, but at a large currents, close to 1 amp, they do cause a voltage drop. That's why I measured them in advance. And I'm now using those leads to connect my bench power supply to the 5 volt rail of the motherboard. First, only the 5 volt rail, 1 rail at a time. There are 4 different rails, minus 5, plus 5, minus 12, and plus 12. I'm starting with plus 5 only. There are 2 pins that have the plus 5 signal. I'm going to use a further away pin from the ground to avoid risk of short circuiting. And now look, I'm going to set the voltage at 1 volt, the current at about 1 amp, and I turn it on. And there is only 1 volt at the leads of the power supply, and I will measure the voltage when it comes into the motherboard, and you see that there will be a small voltage drop. I get 0.96 instead of 1 volt. So there is a small drop, a current of only 19 milliamps that you can see on the PSU. So it's a small drop. Why am I doing this? I'm doing this 1 volt at a time because I want to give the motherboard a chance to have the tantalum capacitors reformed. They are orange. I cannot replace them with orange tantalum capacitors. This is a minimal intervention restoration. So I want to start them slowly so they have a chance to heal instead of putting 5 volts straight on, because then it might just pop like popcorn. And I don't want that. I want to keep the components. So I was at 2 volts and 142 milliamps. Now I'm going to 3. The current increases a little bit, as you can see there. So 3 volts in the PSU, and at the input of the motherboard, 2.4 volts. You see now, because the current is higher, we have more losses on the leads, the little cables coming from the PSU to the motherboard. This is something I actually had forgotten, because I only use my bench PSU with the projects I designed myself, and these are modern circuits, all CMOS, very low current consumption. But when you get to hundreds of milliamps, the loss on the leads can be appreciable. Look, 3.15 volt at the motherboard, while the PSU is putting out 4 volts. So we are losing more than 0.8 volts on the leads of the PSU. And I'm showing this to you in real time, so you get a feeling for how long I wait. Now I finally got to 5 volts. So it's more than 700 milliamps now. And on the motherboard, we only have 3.9 volts. So more losses on the PSU's leads. This confused me at first because I forgot that the leads have a small resistance. So there are losses on the leads. Measured for the first time late at night, and there was this difference between the PSU and the motherboard, and I was like, where did this come from? And I left it and I just went to bed. And next day I came back in the evening and I realized, of course, the leads. Now look, 4.6 volts on the motherboard, while the PSU is pumping out 6 volts. So I want the motherboards to be at 5 volts slowly, so I will have to boost the PSU's voltage even higher. It will go to 6.5 volts actually at the PSU, and then the motherboard will be at almost 5 volts, but not quite yet. So you see, less than 1 ohm resistance in the leads can cause severe loss of severe voltage drop on the leads if the current being passed is large enough. So increase the limit to 1.5 amp. and put the voltage at 6.5. I turn it on. So I get a current draw of about 1 amp, 1.019, and look at the voltage on the motherboard. Not even 5 yet, but close enough. I'll stop at this, 4.916 volts at the motherboard, while the PSU is pumping out 6.5. Yeah, that's what you get. But anyway, the board is now started up properly. The tantalum capacitors on the 5-volt rail are not going to blow anymore. Now I have to do the same thing on the other voltage rails as well. So this is what's happening. The PSU is putting out 6.5 volts. Now we measured more or less the resistance of the leads. There are 2 leads, so one of them I'll call R1 and the other one R2. And we measured more or less, taking into account also the resistance of the multimeters leads, which is about 0.2 to 0.3 ohm. So I estimate that one lead will have a resistance of about 0.9 ohm. This is just a rough estimate. You can't have a precise value here without measuring it properly. And the other one about 0.7, so 0.8 on average. We saw the PSU showing us that the current circulating through the circuit was just a tiny bit over 1 amp, 1.016 amp. And now from Ohm's law, we know that the voltage drop on a resistance is the resistance times the current. So the voltage drop on the first lead, V1, is the resistance, 0.9, times the current that goes through it. So we get 0.9144. I mean, these many numbers after the decimal point is ridiculous. We don't have this precision, but just putting it all out there. And the other one, the same thing, the voltage drop in V2, which has the same current I going through it, is the resistance, 0.7, times the current going through it. So we get 0.7112, more or less. Now, what is the voltage drop on the load, which is the motherboard? What is the voltage drop here? Well, we know that because this is what is remaining after we take into account everything else. In other words, VL, the voltage on the load, is the voltage of the power supply minus the losses, V1 and V2. So if you do this operation, the voltage that ends up on the load is only about 4.9, which is what we measured, more or less 4.9 something. So if I round this to 4.9, it explains the result. So although the PSU is putting out 6.5 volts, and although the PSU's leads have a very small resistance, under 1 ohm, you still have a massive voltage drop on the leads, such that you get only about 4.9 volts on the load. So this is what's happening. But the point of this whole exercise was not this. The point of the whole exercise was just to put voltage on the motherboard slowly, instead of going to 5 volts immediately, going to 1, to 2, to 3, to 4, to 5. But of course, to do that properly, I need to know the VL. And the VL is not 6.5. The VL is much lower. So that's why this whole exercise. And now, since the board is already powered up at 5 volts, no reason not to check the oscillator and the I/O of the clock divider to see if the board is alive. And it is. We have multiple heartbeats. The board is alive, so that's a very good sign. And with the board on for a while, I checked the temperature of different chips to see if anything was getting too hot, and they were not. So I moved on to the other power rails. This is a 12-volt power rail, and then there is the -12 one and the -5 one. I'm just showing the 12-volt power rail that I'm bringing up from 0 to 12 volts, 1 volt at a time, in order to give the decoupling capacitors on the 12-volt rail time to heal, time to reconstitute the oxide layer instead of popping like popcorn, and everything went smoothly, no problems there. Now I gave the board general service. I'm cleaning here the connections for the cassette deck. And then it's time to repopulate the board. I put the oxide on the pins of all the main chips. I cleaned the sockets as well, as we've seen in the previous episode. And I put everything back in, ready for our first integration test. Putting the chips back in the socket is delicate. You have to be very careful doing that. The whole thing is old and delicate. Now, the same way we brought up the tantalum capacitors in the motherboard slowly, so they heal instead of popping, there are tantalum capacitors in the PSU as well. So I used a variac, or a variable transformer, that red thing you see there, and I'm bringing the input AC voltage up from 0 to 110 volts very slowly while I measure the output rails of the power supply. This is the 5-volt rail, and you see it's growing, it's getting slowly to 5. The input still at 70 volts AC, it should be at 110, but it took me more than half an hour to bring it up very slowly up to voltage. By the time you get to 80 volts AC input, the 5-volt power rail is already regulated at the final value, 4.956. That's the final value. The 12-volt and the minus 12-volt, they are also pretty well regulated. So any extra increase in the input AC voltage just maintains the output voltage where they are. And the PSU now has been brought up to voltage slowly. None of the tantalum capacitors popped. So I'm now going to check for the ripple. Remember, to see if the capacitors are working well after I have reformed them, we need to check the ripple. And look at that. There is hardly any ripple. Each square on the oscilloscope is 50 millivolts. We want the ripple to be under 50 millivolts peak to peak, and it's well under, so much so that I even checked on the multimeter. I checked for AC and it was giving me 0. It's an excellent power supply. The capacitors are excellent. There is hardly any ripple at all. We are totally good to go. Now, with the power supply already working for a while, I also used my laser thermometer and I checked the temperature of that little transistor that had a radio heatsink. And I was getting about 50 Celsius. That's a very hot day in the tropics. It's not dramatic. Everything connected to the main chassis as heatsink was running at 24, 25 degrees Celsius, no problem. But there was another transistor without heatsink that was running at 53, 55 Celsius. That's still a hot day in the desert. But yeah, I'm going to add a heatsink to that transistor, even though it was not in the original, because it's a safety issue. 53, it will reduce the lifetime of that transistor, and it's already old. Later on, I will add a heatsink there. I have to buy one. I don't have one as I'm editing this yet, but it's on order. Okay, now we have to put everything together. I have to connect the video cable, the composite cable. In my case, it's an RCA cable, but the output is PL259. So we need an adapter, or PL259 male to RCA female, and that's what I just connected there. So the video is now connected. I'm just lubricating a little bit more the connectors from the PSU to the main boards, to the motherboard. Make sure everything is clean. So I'm connecting now the power rails of the PSU to the motherboard, cleaning the UHF cable, which brings the composite video to the back of the computer. Motherboard still loose, but that's good enough for a test. So let's turn it on and see what happens. The screen in blue at the back, that's the screen I'm using. And we get a black screen. We should see a cursor and a prompt, but I only see black. So, okay, I didn't expect this thing to work straight out. So the obvious next step is to turn on the oscilloscope and check if we actually have a video signal at all. That's what we have to do next. So I turn the oscilloscope on, and lo and behold, we have a perfectly well-formed composite video signal. There is nothing wrong to it. It's mostly black, as it should, but I still don't see a cursor and a prompt. Okay, now let's check then the pins of the CPU where everything converges. And I measured everything, data bus, address bus, all the control lines of the 8080A, and there was nothing wrong with it. I couldn't see anything wrong at all. Everything looked just right, just fine, including the power rails. So I figured, well, I didn't test the memory chips. It's the only thing I didn't test, and if the memory chip is not retaining data correctly, it would be consistent with a well-working CPU. It's just not reading or writing the correct data from RAM. So I took each RAM chip and I put it through a little tester, because these are SRAM chips. They only require 5 volts. So you just need a little Arduino sketch. And somebody already made a sketch, wrote a sketch, and made it available online, Martin from the Czech Republic. I put a link to his webpage below. You should check the comment section of his page as well, because he uses a header that he didn't make available, but he pastes the contents of the header in the comment section. So you should look at that. And it tests everything for each SRAM chip, the addresses, the values, and whether it retains the values correctly. And every single SRAM chip passed. So I was baffled. Why is it not working? And then I remembered that, well, I didn't test the ROM in the personality card. And if you remove the personality card, the computer is supposed to show a screen filled with characters, 0 and 9s, if I remember correctly. So I went ahead and I pulled out the personality card to see what I would get. At least I eliminate that potential source of error, that little ROM chip there. So turn the computer on and see if I get a screen full of characters. Lo and behold, I do. It's just completely off center. And that's why I was not seeing the cursor and the prompt. They were just out of the screen, and there are 2 little potentiometers on the motherboard. And if you adjust them, you can recenter the image. You see? I just recentered it. And so everything seems to be working well. It's out of the frame. You can't see what I'm doing, which potentiometers I'm turning. So I decided to make a little handheld video so you see what I mean. At the very front of the board, those 2 little potentiometers, if you turn them, you just move the image on the screen horizontally and vertically, so you can recenter the image. And now I'm thinking, if I put the personality card back, I'll just see the prompt and the cursor. They were just out of the field of view because the potentiometers were not set properly. So that's the obvious next step, to go ahead and turn the machine off, like I just did, take the card, insert it back in its place, and now that the image is properly centered, we should be able to see the cursor and the prompt, because everything is working. Everything was tested independently before this integration test. So unless the ROM is busted, we should see. And there we go. There is the prompt. Sorry, it's out of focus, but there it is, the cursor and the prompt. So I was still in the process of restoring the keyboard, so I didn't have the keys restored yet. But I just connected the main board of the keyboard, because it's a capacitive keyboard. And our body has picofarad level capacitance. So if I just put my fingers on the pads, I should be able to type. And there you see me typing. You see those little pads respond to a capacitive load. So my finger has enough capacitive load that occasionally I manage to register a key press. So everything seems to be working just fine. And the motherboard and the PSU are working fine. Every chip is now tested. The keyboard seems to be working fine as well. At least there is no catastrophic error. But I'm still busy with the restoration of the keyboard and the restoration of the case, which I already did. And you already saw the result in this video, but I didn't show you the process. So I will cover the restoration of the case and the keyboard in the next episode. But the PSU is done. The motherboard is done. I just need to add a few things, like maybe swap one more chip in the motherboard, that chip that was bringing down the impedance of the 5-volt rail to ground. It's still working, but I want to swap that one, the 4th one, and I want to add a heatsink to the power supply. Other than that, it's all working. So thanks for watching, and I'll see you next time.